So welcome everyone to this webinar on assessing the feasibility of heat pumps for horticultural greenhouses. We've got a lovely 1-hour webinar for you this afternoon and hope you enjoy it and get ready for a little bit of interaction at the end. My name's Jared Leake and I'm the CEO of the Australian Alliance for Energy Productivity. And we'd like to start this webinar with an acknowledgement of country. We would like to acknowledge the traditional custodians of the country throughout Australia and their connections to land, sea and community, and pay our respects to their elders. For those of you who are new to A2EP, the Australian Alliance for Energy Productivity, A2EP is much easier. We're a non-for-profit energy association which is focused on energy productivity. And for those that aren't familiar with that term, that's very much about getting more value out of each gigajoule that you use. And so instead of just looking at saving energy, we're very much about how do you get the most out of energy and get the most value out of that. And these are our wonderful members that help support the work that we do, and they share our vision of improving energy productivity in Australia, providing smart and fast decarbonisation. Just a little bit of housekeeping to get us underway. So we'll be recording this presentation and issuing that to you sometime later in the week, along with the slides. Time permitting, we'll have a quick Q&A at the end, and we're certainly planning to and hoping to do that. And so feel free to populate the Q&A box. So if you press that Q&A button and start typing in there, you can put your question in there, and we'll have our presenters answering that as we go through the webinar as well. So yeah, feel free, throw something in there if you're not too sure. Please, it makes it much more enjoyable and happy to make it interactive. So please put those questions in the Q&A box. And you can feel free to have a bit of a side chat as well on the chat there, but we'll be focused on that answering questions in that Q&A. Just to kick us off, I'd like to hand over to Katrina Hill, Regional Development Officer of VegetablesWA, and this is the VegetablesWA being the sponsor for this program, and just give us a little bit of grounding of how we got to here. Over to you, Katrina.
Thanks, Jared. Hello, everyone. Yeah, I'm Regional Development Officer with VegetablesWA, delivering the Vegetable Extension Network program. One of the key focuses of our project is input efficiency, and the project goal was to determine the physical and financial feasibility of adopting heat pump technology and associated technologies such as solar or thermal storage on 3 unique greenhouse sites in WA with growers, Zeke, Doug and Alex. The project was funded by the Vegetable Innovation Fund and contracted to A2EP, and then subcontracted with assistance with DETA Global and Energy Smart Water.
Thanks very much, Katrina. I was honoured to do this job with VegetablesWA. A2EP is doing a lot of work with heat pumps and renewable heating over the last 5 years. Lots of different publications, and I think we're up to about 30 or 40 different feasibility studies that we've worked with there. And we certainly know that that heat pumps are an excellent technology, a great technology choice for heating, but the application of them and how to get them right and what have you, that's still a growing area there. And so that's why we're very happy to go these studies and really help that and work with the people that we know understand the fundamentals of heat pumps and how to get the most out of them. Just to give you a little bit of a grounding here, heat pumps, think of it like a reverse cycle refrigerator. Instead of you're trying to produce cold, you're trying to produce heat. And so that's the concept. And with that, you get a very good, what's known as a coefficient of performance, typically running at 300, 400% efficiency when you move heat from one place to another, rather than actually trying to create energy, so to say. And so that's why that's a very good technology to look at and why they're getting so much focus around the world. In terms of the operating costs, it can be much lower, especially if you've got on-site solar PV, which can typically deliver you electricity below 10 cents a kilowatt hour. Then they become really quite economical to operate. And thirdly, it's lower CO2 emissions, especially when you are using renewable electricity and you're displacing things like LPG or natural gas or even biomass, really. If you're burning biomass but compared to a heat pump using renewable electricity, you'll have lower emissions as well. So we see it's a very good solution. It can be very economical. The market is growing, so I thought this is definitely worth some of these studies, and we've got some good results to share with you today. We did also look through these studies at biomass boilers and electric heaters and the different types of heat pumps, that being ground sourced or sort of like a geothermal type of heat pump. You've got air-to-air heat pumps, and think of that like your own air conditioner. That's an air-to-air heat pump. Or you've got air-to-water heat pumps where you may be trying to take some heat out of the air and heating up some water. And it's this third type that was found that was the most economical and provided the best returns, it looks like, in this glasshouse type environment, protected cropping environment rather. And so you'll see that as we go through the studies and the results from those. So why consider the heat pumps and more heating and things? We saw this across the studies where the yield improvement and quality, potential to save money, and you'll see that again in the studies that each of these ones have that opportunity to save money, and we see the increasing costs of LPG and natural gas and what have you, certainly making it more viable to use heat pumps as well. Fuel availability could be an issue for you if you're having struggle getting that biomass consistent supply throughout the year. Okay, then if you change to a heat pump, that could be a good solution there for you as well. And finally, with the carbon footprint, there's a demand to decarbonise, and if you haven't got that pressure from your customers now, you can certainly expect to do that with the likes of Woolies, Coles and Metcash and what have you, all planning to be pushing out carbon reduction through their suppliers. So it's on its way. So joining me here today, we've got Hamish Hendry from DETA, along with Glenn Schultz, and Chun and Peter Teoh from Energy Smart Water. So they'll be presenting each of these cases here today. And these are the farms that we were able to do the studies with. So that was Zaldish Farms, and we do have Zeke online today. So if you've got any questions for the grower, you can absolutely ask Zeke, and we'll take that at the end. At Zeke's farm, they're using LPG. The other one we looked at was Stake Hill Produce, and they've got a biomass boiler. Now, Alex couldn't join us here today. And the third site was Grown Smart Produce with Doug Chamberlain, and they currently have no heating, so not able to get that higher yield in winter. And that's very much part of their business case, is having to look at getting more yield through winter. So it was quite interesting the way it worked out, having three different options there, with one with LPG, biomass and no heating. And so that gave us a really good picture of the different challenges and issues for those conversions or new adoption, as it were, for the no heating case. And with that, so I'd like to hand over to Hamish and Glenn at DETA, and they're going to take us through the very first study here, and that is for Stake Hill.
Yeah, g'day. My name's Hamish Hendry. I'm an engineer at DETA Consulting. DETA Consulting is a carbon sustainability consultancy across Australia and New Zealand, and we sort of specialise in heating systems on industrial sites and stuff like that. So with these two sites, we conducted some site visits, went away, crunched some numbers, and produced a couple of reports around the feasibility of these heat pumps at these two sites. And provided some good stuff, because two very different sites with different heating systems and different opportunities and challenges. So a bit of a site summary. So this Stake Hill was located in Baldivis, which is south of Perth, and was a covered greenhouse site growing tomatoes. The site consisted of 3 greenhouses, with each having individual heating loops fed from a centralised boiler system, which was utilised to maintain a minimum temperature of 17 degrees throughout the heating periods, which is during winter and overnight. Originally, the site consisted of about 6,500 square metres of enclosed greenhouses, and utilised a 1.2 megawatt coal boiler. This was then expanded to about 9,500 square metres, and at the same time, they converted from coal to biomass. And this had the effect of reducing the output of the boiler by about 20%. And that's just because of the calorific value of biomass is a little bit less than coal, and the actual density of the fuel is lower, so you can feed less of it into the boiler. So we estimated that dropped the output to around 550 kilowatts, give or take. And essentially this had the effect of reducing the sort of thermal capacity per unit area of greenhouse. So they started having some troubles with maintaining that 17-degree temperature, and they were fortunate enough to be able to acquire some hot water tanks, which they use to store energy. So during the day, when not requiring the heat, the sun shining, they were able to heat those tanks up and then distribute them, empty them during the night and supplement that heating system. One thing we did note on this site was that throughout the heating periods, it was actually quite limited through the year. The biomass system that they used had some potential fire risks that, wasn't so great. And it was also identified too that the system was becoming near an end of life. So the reason the study was done for Alex was to be able to identify some alternative options for the biomass system that would be good. Down the bottom there is a bit of a breakdown of the current consumption and the total cost and the unit cost for fuel and the emissions associated with the biomass. Just go to the next slide. I'll put that thing up as well.
Next slide, please, Jared.
So we investigated two solutions. A base case scenario, which looked at a heating system that could deliver a similar output to the existing system, and an expanded system, which looked at potentially covering all of the heating loads throughout the year. From investigation, we were on site, the increase in 9,500 square meters in the current system, it did potentially struggle at some points in the year, and that's why we looked at that expanded scenario, and we sort of estimated that to be around 1.7 megawatts of load. So the company that provided quotes for us was Motokawa, who they provide lots of industrial solutions for heat pumps around the place. And system we looked at was the heat pump would be put in a specialized container system with all of the correct refrigerant and ammonia safety systems, and that would be tied into the existing distribution infrastructure sitting next to the existing system, which then could have been left for redundancy or got rid of, which just made it easy. Unfortunately, we sort of didn't really look too much further into that expanded case scenario, because being a bespoke dual stage system, the capital costs were about 40 to 50% higher. So sort of only investigated the base case scenario on those financials. Next slide, please. So the total project costs were quite high, coming in at about 1.4 million. And the reason for this is industrial heat pumps are quite expensive, but also the site was limited on its electrical capacity. And that meant that they needed to go through a series of studies and different contractors to be able to increase their site capacity. So I think their existing was around 70 kVA, and that potentially needed to get upgraded to around 335 kVA transformer, which the turnaround that's 18 months, and the costs were in the hundreds of thousands. So that wasn't the best for it. And also included in this cost here was Osborne consultancy. The engineering and indirect costs were a big part too. So project management, design, and contingency. So this is portraying sort of a worst case scenario. And through investigation, unfortunately, due to their very low cost of biomass that they're currently acquiring, the net energy savings were actually negative. So they're acquiring biomass currently at about 4 cents kilowatt hour compared to 29 cents kilowatt hour, which is quite high. So with the COP of the heat pumps, the effective rate would have been about 10 cents kilowatt hour, but still it's not comparable with that current biomass cost. And that resulted in a net present value of about negative 1.1 million. But the main thing to point out here is what we are doing is we are comparing the current system against a new system, and the only energy savings we're considering is the energy savings. So what should be done in the future is that if that system needs to be replaced, the heat pump should be considered against sort of all other alternatives, such as new biomass boiler or a LPG boiler or that sort of thing. And also a big part of that's the carbon associated too, which should be a consideration. And yeah, obviously the heat pumps, the electricity are much more safe, I want to say, supply of fuel. It might be a bit more consistent over in WA, and it also doesn't provide those fire risks that the current system does. So yeah, next slide, please. And yeah, here's just a few challenges, opportunities that we sort of identified on these sites, or on Statefield, sorry. So one thing we did find that there was good metering and good controls to a certain extent. One thing that's helpful for us when we go to these sites is lots of them have water temperature going to the greenhouses, but lots of them don't have the flow or temperature returning. And if we have that flow, the temperature out and returning, we can make an inference or understand the heat that's being inputted into the glass houses or greenhouses. And then we can compare that to the actual temperature within the glass house, and then a correlation will be made, and a more effective process can be done to size those heat pumps, which is important too, because small increases can mean a large increase in capital. So getting that right could mean quite a big reduction in your capital expenditure to put in one of these heat pumps. Obviously, as I was saying before, the electrical capacity upgrades are quite high, and this is quite a specific case here because a large centralized system requiring that large increase, is expensive. And again, the capital costs associated with the heat pumps. The one thing, again, pointing out, the current electrical contract pricing was rather unfavourable. So that 29 cents was what they're currently paying, and the potential network cost increases they'll incur from supplying more electricity to the site. So,
because it was under a residential contract.
Yeah, under residential contracts. Whereas if you compare that to maybe a larger industrial site that uses a lot more electricity, you might find that those contracts are a bit more favourable and reducing the costs associated. And again, sort of comparing it to industrial sites, comparatively, that utilisation of heat pumps throughout the year, you're only using it for a winter period. So you're only using it for maybe 6 months to 8 months of the year, 4 months of that year, you're not using it. So if you're using that whole period, your fuel costs are higher and your potential paybacks are better because of the COP you gain from those heat pumps. And then obviously a few opportunities is the fire risk is mitigated essentially for the heat pumps. The electricity is a more reliable fuel source than biomass from what we can see currently in the Western Australian market. You get that efficiency of heat pumps. Yeah, the increase in that electrical consumption may mean that they can get more favourable contracts, and the heat pumps compared to that current system, I'd say we could probably get better controls and tighter temperature control, which may or may not lead to improved yield and further a better payback for those heat pumps, making them look a little bit better. And lastly, for the site, just want to point out that, so we did a bit of a sensitivity analysis across the cost and the energy savings, and we found that I think a 13% increase in the biomass cost would mean that MPV was cost neutral. So comparing that to what they've seen the last year or two, I think they've seen about a 75% increase in biomass costs. So it's currently pointing not the greatest picture if you're looking at an MPV, but it's almost there, and there's a few things that would just flip, and the heat pumps would be a great technology to be able to implement on site.
So it sounds like they're lucky they got cheap biomass at the moment, but that may not continue. Yeah. They're unlucky because the electrical connection was maxed out. Maybe some on-site solar PV could have helped them. Yeah. So just making those a little bit harder for the case there for Stakehill.
Yeah, and I think a good point to bring up too is the as they've got that thermal storage there, if they had a good amount of land for solar, that thermal storage is really well set up. And I think there was a question there about solar during the day. If you've got that large thermal storage, you're able to generate heat with the free electricity during the day, store that in those tanks, and then that's able to be supplemented to the greenhouses in the night when you're not generating solar.
Yeah.
Yeah, and the second site we went to was Zaldish Farms, and this was located at Oakford, so again was in South Perth, and this was another covered greenhouse site, and they grew capsicums. So the site consisted of 6 different greenhouses of varying construction. I think there was 2 polycarbonate, 2 polyethylene, 2 glass houses, I think, and the focus of the study was greenhouse number 5 at the site. So this greenhouse, they utilised commercial or these residential Rinnai LPG hot water heaters. So they had 8 in total across that whole greenhouse. So the greenhouse was split up into 2 heating zones, each of them utilising sort of 4 of these units, with one mirroring the other. So each was about 45 kilowatts, totaling 360 kilowatts for the whole system. One thing we did note for this site was they were using black irrigation pipe, which is great because it's very easy to work with. But comparing that to some other sites, we've seen the steel and other methods of doing it have got better heat transfer properties. So it's easy to work with. So trade-offs, I suppose. It's easy to work with, but you don't really get that good heat conduction you would have out of a metal substrate. But yeah, so this site, they're circulating water at 35 degrees through these systems, trying to maintain a 18-degree minimum set point throughout the night. One thing on this site here, we did notice that the LPG units, being the residential ones, sort of out in a sort of coastal-ish zone, sandy environment, the units did show a lot of corrosion, and I think Zeke mentioned that these units did have to replace quite often because of this, the issues they've had there. So that table at the bottom there is their site total usage between electrical and LPG. The greenhouse number 5 used about 260,000 kilowatts of LPG and emitted about 57 tons of CO2. So the system that we came up with, alongside some of the suppliers, were 3 heat pump units, 3 air source heat pump units. So this system comprised about 500 kilowatts and about 165 kilowatts each. So this is slightly more than what they currently have installed, and the reason being that a third smaller unit could be used to sort of align it with the same system, but the sort of cost to get a larger system, the incremental cost wasn't that much more to get a bigger system. So we sort of went with that, and from looking at some of the data, we identified that it did struggle a little bit in some periods to be able to maintain that 18 degrees. So the 500 kilowatt would have aided in helping them there. So along with that system came a buffer tank of about 4,000 litres, and that tank there is not so much a thermal storage tank, but more of a system to stop the heat pumps and short cycling, if that makes sense. So move on. The system we looked at also increased the water temperature that circulated to the thing. So the maximum temperature of these units was a bit higher than what they currently have. Again, maybe would have helped or will help with that driving force to get more heat into the system. We did investigate some hot water storage for this site, but we found that the cost comparison between a third heat pump or 2 heat pumps in the hot water storage tank was about the same. And this site sort of, I don't think, had the greatest area for solar, so that solar offset for thermal storage maybe not have been as great for this site compared to the previous Seiko site. So the total project costs here, we came up with about 192,000. with most of this cost attributed to the installation and supply of the heat pump. So the units we specified were about 52,000 per unit installed, and the rest of the costs being those sort of indirect costs around system design, project management fees, and some contingency in there. This site here, we saw about 18,000 per year for that greenhouse in energy savings, and that's again with that quite high cost for the electricity, but compared to the LPG, it's a bit better than the previous site. It's important to note here also that some units can probably be obtained cheaper, and again, the costs that we have shown here are probably on the top end worst case scenario, but we've gone with some reputable suppliers. So here's AHI Carrier, and we've got those indirect costs applied there. So we're just trying to show that worst case scenario, and majority of the times it will probably be better than that. And again, so the net present value here is negative, and that's because of that low LPG cost. But we did the same things. We did a bit of a sensitivity analysis, and we found that a 2-cent increase in the cost of the LPG would then make that net present value 0. And that's just comparing that to the current system, no replacements or anything like that. So if you went and compared that to other replacements, then that would get even better. Next slide, please. And then again, we just had a few challenges and opportunities associated with these sites. The current low cost to replace those LPG heaters. So the residential, I think they're very cheap to replace and easy to deal with. That high electricity cost we're seeing is a bit of a trend currently in the WA. Again, the high cost of the heat pump systems in comparison, and then that low utilization again. I think that's important to note in this one here too, is using those commercial units, there's a potential that you can use reverse cycle heat pumps. So essentially what Jared was saying at the start, you're using that cooling side, and you might be able to improve the utilization to provide some cooling to the system, and then have tighter temperature control all year round, which then might be able to increase your yields because of that temperature control. And then, a few opportunities, the increased lifespan of the heat pump. So indicated from AHI Carrier, these units had around 15 years of correctly maintained of lifetime, which is quite good. Get that really good efficiency gain out of the heat pump. So as soon as you start seeing those prices change and all that sort of thing, that efficiency really comes into play, and it really reduces your costs. This site too, because they were using LPG, they had a decrease in their carbon emissions associated with it. So there's a potential they're eligible for ACCU funding. I think that over the lifetime was around $10,000. And if WA sort of came into and started their own sort of carbon or efficiency credit system, it might be even better, similar to the VEEC system. And again, talking about that reverse cycle. And then lastly, the future proofing for the grid emissions, and currently less carbon emissions is quite good.
And Hamish, we've got an interesting development since you completed the study a month or two ago. The site's actually gone ahead with a heat pump installation. They're going ahead.
Yeah, it's great news, eh?
Very good. And they did manage to get those costs down. They've taken on a bit of the scope themselves, I understand, and what have you. So it's great to see that the study led to a bit more confidence in them going ahead with heat pumps, which is great. So we'll be watching that one, see how the performance of that one goes, and look forward to sharing that one as well. And we do have is it Zeke online? We could answer a few questions on that one at the end of the webinar as well. So very good.
Yeah, and it's probably one last point too I wanted to point out for these sites as well. They're all doing things great, but one thing to bring out about sort of heating systems is there's a lot to do on the demand reduction side before you move to sort of fuel switching and stuff like that. So by reducing what you can do on the demand side, so improving your distribution systems or some shades and stuff like that, then that might provide the opportunity to again reduce those system sizes, which then affects your capital costs, which again makes that system look even more commercially beneficial.
Excellent. Hamish and Glenn, many thanks for that. Let's move on to our third and final one. We'll be back to you at the end for any questions as well. So stick around with us. Now moving on to Energy Smart and Water, the study they did for Grown Smart Produce. We've got Teoh and Chun here presenting their findings from their study.
Hi everyone, good afternoon. Thank you very much, Jared. Thanks for the opportunity from VegetablesWA and also A2AP. And we're working very well with Smart Grown. Thanks, Doc. So our team have go through the feasibility study on this site at 60 kilometers north from the city of Perth. So basically the site itself, they consist of 4 greenhouses. So it's a cucumber plantations. So each of the greenhouse have about 7,000 plants in each of the greenhouse. So total of 28,000 plants. So at the moment, there's no existing heating system on the site. And the owner is looking for heating solutions to make use of to increase the yield during the winter month to grow on the summer variants. So that would help to increase the productions, and also the price during the winter are much better compared to summer because of the demands of the cucumber. So on the site, we noticed that there's opportunities that we can put in solar PV. So yeah, our main purpose is to able to make use of the solar generation during the day and do a solar soaking on it and to manage the demand and response. Next slide, please. So the challenge at the moment on the site is because there's no heating, and then we don't have any heating load data. We don't have the baseline to compare, so we have to run on the simulations or on to create a baseline. So, but right now the owner itself is started to collect some temperature data on the greenhouse itself, and then yeah, this is also we saw the benefit is to, like what I mentioned before, we can create a situation that during the winter, and then the greenhouses act like a summer situations to create more yield for the growth. And we find out the cucumber price fluctuate a lot during during summer, where there's a lot of supply in the market, and it dropped from $2 down to 60 cents each. And yeah, so what the assumption we taken from here is we can see historical data where we collected from the weather stations on the area that temperature are pretty low during the winter, and that's the part where we see opportunity that we can help the grower. And yeah, so we can see that the areas covering the whole place are pretty big. So they have a similar thermal property throughout all the 4 greenhouses. So what we can see here, if we want to run the project, we can do it on 2 greenhouses to see, and then this one would bring it would be a modular system that we can put on. So what we do as well is, because winter, summer, the variants are pretty big, we calculate on shoulder months as shoulder season as well. So we use those kind of simulations to predict the productions and also the price of according to the market in WA. Next, please. So yeah, the opportunity is if we can simulate that kind of growth for winter month to grow summer variants of cucumber, we can see if, let's say, the price at the lowest selling price and lowest yield, that is the risk calculation we took on. That you can see there's a increase of revenue about almost 400,000. If we look at the positive side of the yield, means we have high selling price, high yield with this kind of upgrade. Annually, the revenue will increase to 700,000. So it's from, you can say that the return on investment would be about the best yield, best pricing you will get about below 5 years return on investment. If, let's say, the worst case scenario, low yield, low pricing, you might get about 9 years plus to 10 years. And what we look at this site is we want to make use of the location where we can use the solar during the daytime and run the heat pump, and then we do a thermal storage. So our thermal storage can store up to 95 degrees, but on this kind of feasibility study, we put it at storing about 55 degrees first. So we can improve that when down the track. So what we do is we store the energy during daytime and also heating up the greenhouse at the same timing. So what happens when come to night, we work out two solutions. One is to run half the load of the heat pump. The other scenario is we shut down the heat pump completely. So we use those energy stored in the thermal storage. And come to the daytime, we make use of the sunlight again, run the solar to run all the heat pump. So that is the best part that we find out. So yeah, so this would help the grower to reduce their scope 2 emission. And also the scope 3 emission, like what we said, Jared mentioned just now about in future, supermarket might request the supplier to have this kind of reduction in the emission. So yeah, this is what we find out. And so we come to a solution. I let Peter talk about the solution that we propose to the grower.
Hi, yeah, this is where I bore you a bit of details. So the system design is essentially focused on simplicity, cost-effective option, and how we can always store the PV energy as much as possible. So in this particular setup, it's a modular 4 system for 1 module for per greenhouse. So each greenhouse will have 2 heat pumps and 4 tanks, which equate to about 20,000 liters per greenhouse to store the energy. So during the daytime, what we studied profile is that the heat pump would charge up the tank, and then after that, how to release the energy later on. The other research that we have done is that how to deliver the heat to the greenhouse, because the greenhouse doesn't have any heating at all. So we need to deliver the heat to the greenhouse or to the plants directly. What we find is like through our modeling is that a pipe underneath the tray, as you can see in the middle picture there, that if you put a pipe underneath the tray, the radiant heat and the convection heat able to hit the tray, and then they transfer the heat to the soil. And we find this is a with a quick experiment what we've done in our workshop. This is the best method we can find out to increase the temperature as fast as possible and maintain the temperature throughout the nighttime. On the right image that you can see approximate layout of the PV. So that's quite substantial, about 360 kilowatt hour of a PV system that we place on the ground. That's where on the north facing hill that the panels be placed on the hill to face it. This is what Doug would want to place a PV, ground mounted PV there to offset the heat pump consumption, electricity consumption. We're going next slide, please. So what we have done a bit of profiling in terms of energy profiling. So what we find out is that the winter peak load happens around 3 a.m. to 7 a.m. That's during the nighttime. So we're thinking how to shift that solar to nighttime, and then the thermal storage play a big role to store the energy and release it during the nighttime. So during 3 a.m. to 7 a.m., we actually shut off the heat pump and then allow the thermal storage to release the heat out to dissipate the heat to the hydronic field. And then during the daytime, then we switch on the heat pump again and to charge up the thermal storage. So you can have you can see this like on the left-hand graphs, you can see this on off during the morning, then on during the daytime. And then on the right-hand graph, you can see the charging profile where the red line would be the yellow line is the PV, and then the blue line is a net consumption, and then the red line is where you see this is like what the power consumption without the PV. So we concentrate the charging during the daytime. Next slide, please. So what we find that the financial outcome of that is this like on a high sales scenario, the payback period is 4.8 years with IRR of 25%. And then the low sales scenario is 9.4 years, IRR of 3%. So you can see this is what would be the maximum and the minimum. Ideally, the return will be somewhere in between. So moving from here, what we'll do is we implement the system for the greenhouse 1 and 2 to test out the system and to fine tune it further, how we can improve it for greenhouse 3 and 4. In order to offset, I guess, to reduce the risk of the low sale value, we'll be looking at a government grant to how to assist with the capex to reduce the capex further, so that if for whatever reason, if it falls in the low sale value, at least that risk is protected. And then looking further from here as well, how to explore how to maximize the heat pump utilization from during the summer months as well, because we have the opportunity to provide cooling in the summer months to protect the crops further from overheating in the greenhouse, and using only solar PV generation during the daytime as well, which is perfectly lined up for cooling operation during the summer months. And then the next slide, please. So we'll say, how would that apply for the grower? So yeah, so this is part of summaries that what we're trying to find out is heat pumps tailored are site specific. If you don't have any heating, this is for you. So a PV heat pump and a good load control is a very good way to provide effective heating, and essentially we look into how to look into effective cooling as well for the greenhouse. And one of the reminders is you're part of the Scope 3 emission compliance for the supply chains as well. So your Scope 2 is your client Scope 3. So this is a good opportunity for you to reduce your Scope 3 emission in order that you help assist your clients to reduce their Scope 3 emission as well. That's it.
Excellent. Thanks very much, Peter and Chun. The space that was required for the solar PV, are you able to put how is that relative to the greenhouse sizing itself? Is it if I've got 10,000 square meters of protected area, do I need 10,000 square meters of solar PV? It looked from the little image there, it looked like it might be a similar amount that you need for your solar PV to drive the heat pump.
Yes, it is. For Doug, he's very fortunate that he got the available land size that he wants to maximize the PV input for the greenhouse. So he already got that space to go with, and he'll just maximize that space for the heat pump. And it worked out to be that ratio, almost the same ratio of the heated area versus a PV as well, which is great, because it's in that case, and we can see that the profile of, especially the winter profile, it fit very nicely within for his location, fit very nicely to offset the PV consumption. In fact, he actually reduced 47% of his heat pump consumption.
Yeah, I think the other thing is because we focus on root heating, not the space heating. So for root heating, I think we calculated that it saved 68% of energy usage compared to the whole space heating for the greenhouse. Mm-hmm. So that is very important.
Very important. Great. And I understand this is the good news from this study as well, that Doug's going ahead with doing some more testing and what have you. And that might be actually a good one to put a question there if Doug is available. So how's that? How are you going with that, gathering the data, and maybe just share a little bit, Doug, if you can, on how you're going about getting that more data.
Yeah, thanks a lot. We've been collecting the data now for going on 4 months. We're actually doing it in 4 locations in 2 different sheds. In one of the sheds that we're anticipating, plus also a baseline study on the other shed. That's collected at ambient outside the shed, ambient out the bag, and then root temperature in the bag. So we intend to carry this through to, well, probably for the next year now. And then just so we've got a baseline to work from, and then we can look at doing trials, either not a full shed, but if not, just a couple of rows in the shed to start with, using a heat pump basis, and then from there, see how we go. So as long as we've got a baseline to start from, I think we'll be pretty much well underway.
Sounds good, and you'll just build this up over time, and that's great. Sounds like a good way to go. Thanks, Doug. Thanks for sharing with it. Got a couple of little summary slides here, then we'll get to some Q&A. So feel free to type a question in the Q&A. I think we've had a couple of questions already answered in there, but we will have time to look at that. This is a few bits and pieces we say to bring all this together. As Chun mentioned, space heating versus root heating. Certainly go for root heating. As you heat up that space all around, you're going to get more heat that just goes outside the building. So concentrate the heating where you need it. And what have you. Measure and check your existing heat load over a season or a full year. That's a great tip there. And hopefully then you can find where you can get that potential for use the cooling from the heat pump as well. But when you have a heat pump technology being a multiple, sometimes 3, 4, 5 times the cost of a simple LPG heater, then you really want to understand that heat load so you can minimize the capex that you have there. Do you have an adequate electrical supply system? We saw that in that one site where that was a limitation. And if you don't have that and you don't have space to put solar PV, that cost really goes up rather dramatically. Thermal storage, I think this is a very important part where you're using that thermal storage, and that's going to be very important going forward as well. You can use more of a solar PV, or as we see tariffs potentially changing to more reflect cheap solar during the day and expensive peaks between say 4 p.m. and 8 p.m. Having that ability to turn off that heat pump, or load flex that heat pump is the term in the energy world, is going to really help with the economics going forward. Mentioned a few times now the co-benefits and looking for cooling and what have you. So that's an important part of it, looking for PV. And one as well is if your existing system is coming towards the end of the life, then think about future proofing and decarbonising, because that certainly that pressure is going to come. We see that the major grocery companies, they're getting their own house in order with their own emissions, and then they're going to be starting to push that down the line, and hopefully they do that in a really collaborative way to help growers transition. And then finally, maybe you can consider some rebates and what have you, and that can typically would pay for around about 20% of the capital cost in most systems, but that's really only Victoria and New South Wales, which have good systems to support with those grants under their ESCIs and VEECs, as they're called in those states. We'd dearly love the other states to get on board with this, but they don't have that at the moment. There is the national scheme of ACCUs, but the ACCUs are rather expensive administratively to kick off and start. You really have to have a decent size amount of energy savings beforehand before the ACCUs are going to be worthwhile. And by decent, I'm talking tens of thousands of gigajoules per year. Very good. So we did certainly found that the air source heat pumps are a great choice and under certain conditions, but yet there's definitely that sensitivity there to the existing, say, biomass cost or LPG cost and electricity cost. Very sensitive to those. Certainly provide a more efficient setup and I think a safer setup they can do as well to the current what's there. But yeah, there is definitely challenging to implementing that, the financial challenges because of the high capex versus the other technologies. So you really got to get that beautifully optimized there. And we've certainly seen from what happened at Zaldish, when you can shop around and look at doing a fair bit yourself, you can bring that capital cost down a long way as well. So are they feasible? We think yes, in the right conditions. If you can include those yield improvements and the value you're getting from that, from the fuel cost, we're seeing the gas prices are increasing nationally. WA has been quite fortunate with holding down their gas prices, but the rest of the country is certainly on that upward trajectory there. Biofuels can have some limitations of supply, or biomass biofuels, limitations of supply, so that can make it a bit harder to get that. And we think that market is developing, and the days of cheap biomass may start closing out a little bit as a lot more people try to decarbonise. So 3 or 4 cents per kilowatt hour for that biomass for those oat husks may not be a long-term solution. And certainly with in terms of the carbon footprint, and you want to be future proof and potentially get a premium fuel product to say it's a low carbon product. This is certainly one way to do that as well. And we've mentioned the capital funding and grants that would certainly assist. And yeah, again, states like New South Wales and Victoria have those things in place that should really help with bringing down that capital investment cost for heat pumps. Good. Let's thought I'll just see if there's any questions. Let me check the Q&A. Looks like a fair few have been answered already. There was a question there. We talked about did we utilise the screening tool, the screening questionnaire that A2EP has developed for these. We did some initial interviews, but we don't see, when you're looking at the protected cropping, they have quite the number of limitations that you do for an industrial site, because often they would have space to put some solar PV, so the space constraints usually not there. And once you've got that out of that space constraint, you can look at putting in solar PV to reduce the electrical constraint as well. So yeah, that's why we had to look at that one. There's a question there about the materials of construction, comparison for OPEX. There's a question there. And Glenn, you maybe just come off mute and take us through that, what you looked at for the OPEX comparison there.
Yeah, thanks, Jared. Yeah, that's obviously quite a short answer in relation to the question. So the OPEX side of the equation was considered in the costs of the heat pump, but not in comparison to the existing operating costs of whatever system was in there in place. So just to bring back to the economics of how this is all considered, what we're trying to do is we're trying to justify quite a large capital expenditure to an ongoing energy supply cost of any existing systems. So there is that large capital component, which we're trying to offset by just pure savings on ongoing energy, which becomes very difficult. But in the scenario where you need to start replacing boilers or other substantial capital equipment, at that point, you're needing to come up with capital anyway. And so at that point, that's where the value, the economics can change rather dramatically. But if you've got an existing system in that's working and it's operating cheaply, it makes sense to stay with that economically, but that only has a certain amount of lifespan. And obviously that's where you need to start planning and for that heat pump change out, because that's that cost going to be incurred at some point as well. So
yeah,
anything else to add on the OPEX side?
Yeah, and I think with being sort of family-owned businesses too, lots of the OPEX on the current systems is done by site people, so you don't really get to see that cost as a monetary value, more as a time thing for people. Whereas for us installing a new system, it's very easy to get a quote from the supplier to say it's going to cost you $2,000 a year or whatever it is to maintain that specific unit you're putting in. So yeah, it did make it look worse because we've only really considered that cost on the heat pump side of things. So if we did account for that, or we did have a way to account for that, then it would have made it look even better for the heat pumps.
Thank you for that one. Question here about we're talking about solar PV, and obviously that is out of sync when you're getting solar production when you need the heat. But I understand that it's quite common in protected cropping already that you have that out of sync, because they may run a biomass boiler during the day to get some CO2 into the greenhouse, but yet then they store that hot water that comes from that biomass boiler and then use that overnight. So it's a very similar situation there. And Glenn, I think you proposed an answer from that one.
Yeah, I did. So happy for you to expand on it, Jared. But ultimately, solar, if you can utilize solar through the day and you can support by generating hot water during that period, when you don't need the heating inside the greenhouse, you can then store it potentially in well-insulated tanks and then draw off at night periods to reduce the thermal load through the greenhouse. And I think Chun and team reference to that in their proposals as well.
Yeah, that's very crucial for thermal storage, where you have to have a proper thermal storage that have the minimum heat loss. So then you can manage the demand and respond.
It was interesting you mentioned before, Chun, about this the temperature that you've planned. You said 50 degrees, but you said you could go up to 90 degrees. What's the purpose? And you just explain that, the idea of going maybe to a higher temperature, because would you send that 90 degrees then goes to the greenhouse?
Actually, we do this feasibility study based on 55 because we want to make it like available for the client to choose on which kind of heat pump they want to use for. And then, but what we can do is, because if they have more generation, or like what we said, if the electricity during the day are very cheap compared to nighttime, so maybe we can make, and in the future, they might build a new greenhouse for the greenhouse and all the things, duty load increase. So if you can store more energy during the cheapest rate or during the peak generation, so we want to maximize that. And during daytime, you know that the weather, you have sunlight and all those things, the greenhouse itself is not so cold. Like what we find out, the most peak demand, peak load demand is during 6 o'clock in the morning. So each greenhouse might need 134 kilowatt of heat generation. So that is where if we can store more energy, of course the COP will drop, the heat pump when it work harder, but it's depend on site. It's very site specific. So it depends on what the site have, what the available on site, and then we design based on the requirement.
Gotcha. And there's also understanding that key part being that solar soak, and we certainly see that in wholesale prices in the likes of South Australia, regularly going negative in the middle of the day, so negative $100 per megawatt hour. So if you're on that, if you're going to get access to that using companies that do the wholesale pricing like Flow Power and AGL and what have you, and NLX, yeah, they can help you be paid to be using that heat pump in the middle of the day. So that can really change the economics there as well. I don't think we see that in WA too much, but certainly see that in South Australia with those negative prices there.
Hey, Jared, can I just add on to that just quickly to reinforce that point? So in Australia, obviously, geographically, I guess we're challenged. We've got all different types of climates depending on what state you go into. So I echo what Chun's saying about each site needs to be considered under its own merits. If we go across the ditch to New Zealand, where one of our companies are, heat pumps are the standard technology that go into greenhouses. There's nothing else to really look at except for, potentially reinjection of CO2 and that sort of thing. So, but heat pumps, because of the requirements for the longer heating program, is a very viable technology over there. And it depends on what part of the country we're in. Those economics will change in Australia. Just add that.
And now, Zeke, I think we've got Zeke online still. And Zeke, while you're there, exciting news with the heat pump coming in. And any ideas when that one's going to be installed? And we might be able to hear about some results from that one.
Yeah, so actually we're just installing. This was our first test about a week ago. And greenhouse empty at the moment, change over season, but in about a week, the new plants will go in and we'll start using recently, I guess. But this is sort of another rollout. So we've already done sort of 5 of our other houses, and this was kind of the last one to do it, I guess. So we've probably over a 2-year period, so we're definitely a big supporter of the technology. And I know probably the one thing I'll say is the running cost compared to LPG is significantly better, and we're heating more, and we can't really measure the production, but we're getting better quality of fruit and heating in times we wouldn't do because of the running cost of the LPG before. But having done a few of our houses with heat pumps, I think as you guys sort of said, that there's like the best case way to do it, but if the capital expenditure up front is an issue, there are sort of cheaper ways to do it, certainly in your first installment or a trial to get the feel for it and sort of reduce that upfront risk.
Gotcha. So just doing this stepwise, and yeah, you're saying you're already seeing that you're going to get some good results from that. So that's excellent, Zeke. So fantastic. And as you decarbonize and hopefully that becomes of increasing value to the sellable product that you have as well. So congratulations, and yeah, well done.
Thank you.
Okay. Well, I'm just going to finish off with a couple of rounding off slides, if you'll bear with me while I bring that up. And so, yeah, thanks very much for joining us here today. We've got these, here's the contacts of the people involved. A big thank you to Katrina at VegetablesWA for sponsoring this program and helping us help the growers look at this technology. So many thanks to Katrina and the team there. Thanks to DETA and Glenn and Hamish presenting today, along with Chun and Peter from Energy Smart Water. They're their contact details there, so absolutely feel free to get in touch with them, or even our Michaela Ling, the project manager, if you wanted some more information. Just to let you know, with A2EP, we've got doing lots of different things on heat pumps at the moment. The thing planned is actually for tomorrow. We're doing site tours around the Melbourne CBD and taking a look at some recently installed heat pumps and going out to a training pod at Automatic Heating to check out their new training pod to look at different types of heat pumps and finishing at the Three Ravens Brewery to look at NX's very exciting CO2 heat pump there as well. So that one's on tomorrow. So we'll be keen to share you all with some photos and the outcomes for that one. So those joining us tomorrow, that'll be great. If you do want more from A2EP, feel free to follow us on LinkedIn or subscribe to our e-news. And that way you'll be up to date with all the webinars and publications and what have you that we put out. But all I can say is thank you for joining us this afternoon. I think we've got through all those questions. If you did have some more, feel free to email them through and we'll get them back to you. We'll have the recording and slides out to you next week. And that's it. Thank you for joining us this afternoon, and thanks to all our panelists.